Welcome to the Chem 1A pre-lab lecture for Experiment 6, using net ionic equations to identify unknowns. Our learning objectives for today is to understand the concepts of weak and strong electrolytes, to be able to identify reaction products, and to learn to write balanced net ionic equations. The final parts of the experiment, we will learn to predict the direction of an ionic reaction based on the products and the reactants. The scenario behind this experiment is that you have 6 ionic solutions, and you know what these ionic solutions are, except you don't know which one is which. So your task will be to combine the solutions A through F, one with each other, and from the reaction products, determine which of the 6 ionic solutions each of these unknown solutions is. It's very important that you fully complete your pre-lab material before coming to the lab class, as you will not be able to interpret your results without first having completed the pre-lab predictions of which combinations will yield products. Ionic compounds are compounds that, when added to water, will split into positively and negatively charged ions. These positively charged ions are called cations, and the negatively charged ions are called anions. For example, if we take sodium chloride, which is regular table salt, and we add it to water, the sodium chloride dissociates into sodium cations and chloride anions. Each particle is surrounded by water molecules, which are attracted to the charge. Because of this, we call the ions aqueous, meaning surrounded by water. Because water is attracted to charge, it masks the strong positive and negative charge of the ions and overcomes the interaction that these ions would have with one another normally. When ions are suspended in water, we call them electrolytes. This is because the presence of ions in water allows the flow of electricity. Strong electrolytes are ionic compounds that dissociate completely in water. Like sodium chloride, when we add it to water, all that is left is sodium ions, chloride ions, and water. There is no more sodium chloride present. Weak electrolytes, on the other hand, only partially dissociate in water. These are things like your weak acids, acetic acid and phosphoric acid. When weak acids are added to water, they partially dissociate, so that we are left with some hydrogen ions and some conjugate base ions, but the reaction is going back and forth between the weak acid and its ionic form. This is indicated by a double-headed arrow. In your experiment today, you'll be combining 7 strong electrolytes and looking to see if they form an insoluble product. This is called deriving net ionic equations. To derive net ionic equations, we look at the 2 chemical species that we are given and think of them as the general formula of AB added to CD, forming the product AD and CB. And what do I mean by this? Well, we can generally think that if we're mixing ionic compounds together, and they are strong electrolytes, that when we put them into solution, they will each dissociate into their respective ions. So if we have an ionic compound where the cation is A and the anion is B, it will dissociate into A plus and B minus. Likewise, if our second solution is a compound of C and D, it will dissolve into C cations and D anions. Because each of these ions is independently floating around in solution, there's equally likelihood that the A cation will encounter its original B anion, and that cation will encounter the D anion. So to see if we will form an insoluble product, we look at our original reactants and swap the anion partners. So now, as a product, we look at A combining with D and B combining with C to give us the products AD and CB. You will next consult a solubility table to see whether either AD or CB is likely to form an insoluble product. If an insoluble product is formed, we will balance the total ionic equation and then cancel out spectator ions to give a net ionic equation. Now let's work through a problem with some real compounds to further cement the idea. So as I mentioned, when you have two or more ionic compounds and dissolve them together in water, they can swap partners to recombine and form new products. And some of these products will have very strong interactions between the ions, and they will form a solid precipitate. So let's look at the reaction of sodium carbonate with magnesium sulfate. So each of these ionic salts are fully soluble in water. They're strong electrolytes, and so they will dissociate into their respective ions. When we are separating ionic compounds into their aqueous ions, we need to balance the ions with the molecular formulas. So if we have two sodiums combining with a carbonate to form sodium carbonate, we should have two sodium ions and one carbonate anion. Magnesium sulfate is 1:1 ratio, so we have one magnesium 2+ cation and one sulfate anion. We will now see how these ions can recombine to form new products. So by swapping the partners, we can see that the sodium would combine with the sulfate and the magnesium would combine with the carbonate. Sodium and sulfate do not form an insoluble product, so these ions will remain aqueous. On the other hand, magnesium and carbonate do form a solid precipitate, so we will write that product as its solid form. Because it is a solid, it is no longer aqueous, and we do not write it as ions. We use the subscript S to indicate that it is a solid. So in this situation, the interaction between the magnesium ion and the carbonate anion is stronger than the interaction between water and these ions. And so water is omitted, the two ions come together and form a solid precipitate. In your test tube, this will look like a cloudy white material forming at the bottom of the tube. So if we consider the ions that did not form this solid precipitate as spectators, meaning they're not participating in the reaction, they're just floating around watching it happen, we can cancel them out from both the reactants and the product side, and this would give us a net ionic equation. So the formula equation for the reaction we just looked at will be written as follows: aqueous sodium carbonate plus aqueous magnesium sulfate would form aqueous sodium sulfate and a solid magnesium carbonate. The total ionic equation is what we were looking at previously, where we see all the ions of the reactants. The ions of the reactants that do not participate in the reaction are still ions, and then the product that is formed, since it is no longer in its ionic form, it's a solid, is written as a molecular formula. So if we cancel the ions that appear on either side of the reaction arrow, we would get the following. So sodium is on the product side, it's also on the reactant side. We have sulfate on the product side, sulfate on the reactant side. And if we look at what's remaining, we can write down the net ionic equation. So that's going to be carbonate plus magnesium makes magnesium carbonate. And that's all there is to it. Let's try another example. Let's say we combine sodium hydroxide with potassium phosphate. We begin by writing out the ions of the reactants and swapping the partners to see what kind of products they'll make. So sodium hydroxide, being a strong base, a strong electrolyte, is going to dissociate into sodium cations and hydroxide anions. Because potassium phosphate requires 3 potassiums for every phosphate, we will end up with 3 potassium cations and 1 phosphate anion. Recombining the cations and anions, we now have sodium phosphate and potassium hydroxide. You can consult your solubility table at this point to see if sodium ions are typically soluble with phosphate ions, and whether hydroxide ions are typically soluble with potassium ions. Before we do that, however, we should also balance the equation. You will see that when sodium combines with phosphate, we needed 3 sodium cations for every phosphate anion. That means we need to add a 3 to our sodium, and because that sodium came from sodium hydroxide, if we had 3 sodiums, we would also need 3 hydroxides, so I also place a 3 here. On the product side, I can see that I originally had 3 potassiums. However, I only had 1 potassium in potassium hydroxide. So I need to add a 3 in front of the potassium hydroxide to balance the 3 potassiums that I see here and the 3 hydroxides that I now see here. Since both sodium phosphate and potassium hydroxide are soluble, these products are both aqueous. In this case, the result would be no net ionic reaction, since the products would look identical to the reactants. They would all just be in their ionic form floating around in our solution. No precipitate will form. Let's try another example. Here we have calcium nitrate and sodium phosphate. I'm going to begin by writing out the formula equation, balancing it, and then move on to looking at my ionic equation. So calcium nitrate and sodium phosphate could combine to form sodium nitrate and calcium phosphate. You'll see that I put 3 calcium nitrates and 2 sodium phosphates to combine to make 6 sodium nitrates and 1 calcium phosphate. To do this balancing, I began by noting that in my products I have 3 calciums. I then placed a 3 in front of calcium nitrate. Because of this, I now have 6 nitrates, so I placed a 6 in front of sodium nitrate. My nitrates are balanced, but to balance my sodiums, I then had to place a 2 in front of sodium phosphate. So we have 6 sodiums and 2 phosphates. Checking with my products, I see that I also have 2 phosphates, and so the reaction is fully balanced. Now that I have the balanced formula equation, I can begin by taking my aqueous components and dividing them into ions and writing the ionic equation. So 3 calciums become 3 calciums. 3 times 2 gives us 6 nitrates. 2 times 3 gives us 6 sodiums. 2 times 1 gives us 2 phosphates. And likewise, I have 6 sodium ions, 6 nitrate ions, and 1 calcium phosphate solid. I know that the calcium phosphate is going to be a solid because when I check the solubility table, I see that all nitrate salts are soluble. However, phosphate forms an insoluble precipitate with calcium. Therefore, in this net ionic equation, calcium phosphate is our product. So the net ionic equation would be 3 calciums plus 2 phosphates forming calcium phosphate. With ionic reactions, there are 3 different types of products that can be formed. The first, like our examples, are insoluble precipitates. And so these are going to be ionic salts that have strong interparticle attractions. So the attraction between the ions is stronger than the attraction of the ions to water. And so instead of interacting with water, they interact with their ion partners and form a solid, just like in our example with magnesium carbonate. Another type of product that can be formed is a gas. If you think about the reaction of carbonic acid and water, we form water and carbon dioxide. This is what we see as bubbles in our carbonated water or soda. Because the bubbles come out of the bottle or beaker, They're no longer taking place in the reaction. The carbon dioxide is leaving as a gas. So it's clearly going to be a product since it is not remaining in the solution. The last type of product is a little harder to grasp and even harder to visualize, and that is the formation of a molecular species. Molecular species are items like weak acids and bases. So in this course you are asked to learn the weak acids, acetic acid and phosphoric acid. It's also very important to remember that water is considered a weak acid. So if the product of your reaction is either a weak acid or water or a weak base, then that is considered a product. This can be a little misleading, however, because weak acids and bases are aqueous since they do partially dissociate. Remember, they are weak electrolytes, so they're still written as aqueous. It's up to you to remember that these aqueous substances are only partially dissociated, so they do form product in part, and they are considered products in net ionic equations. For the last portion of this lab, in the questions section, you'll be asked to predict the direction of a reaction. This is really looking at your ability to identify insoluble products. A reaction will always go towards the formation of a product. So if you see either a solid or a molecular species or a gas given as a potential ionic compound, then you know that that compound must be a product because it would not be a reactant. Products do not react, they come out of a reaction. So if you're given two ionic compounds and either of those, according to the solubility table, are going to give you either a solid, a weak acid or base, or a gas, then that would be the product. If none of these are true, you can consider that the compounds would be reactants. If they are reactants, you should find that you would get an insoluble product. If this is true, then you know that the ionic compounds that you were given are reactants. Okay, a few tips and tricks for when you're going into the lab. It's not necessary when you are combining your solutions A through G to use exactly 2 milliliters of each solution. This would take far too long for you to measure out accurately and involve a lot of washing of your glassware. So for the first couple of tubes, do measure out 2 milliliters with your graduated cylinder. Try to get an idea of how much that is. And then for the subsequent reactions, just eyeball that you're adding roughly equal amounts, around 2 milliliters, of each reactant into the tube. Once you've mixed two reactants together, they might immediately form a solid, but they might also take a little longer to form that solid. So let the tubes sit on your bench for about 5 minutes, give them a tap every so often to mix the contents, and if you still don't see a solid formed, you can place these tubes in a warm water bath and leave them for 10 minutes to see if a solid will form. If after these 10 minutes you still do not see a solid, then you conclude that no reaction has occurred. Once you've completed the experiment, you should find that there were 9 combinations in which no observable reaction occurred. You should also see 9 combinations that yielded a clear solid precipitate. The key reactions in solving which ionic solution is which is by focusing in on which reaction combination produced a gas and which produced a large amount of heat. You should have had one combination of reactants that produced a gas and one combination of reactants that did give off a considerable amount of heat. By looking at which reactions in your pre-lab assignment were expected to give heat and gas, you can begin to decode which solution is which. Remember that in today's lab you will be working with sodium hydroxide, sulfuric acid, and other harmful solutions, so make sure that you are wearing gloves as well as your lab coat and goggles for best safety practices. The amount of heat that will be formed in the reaction is not enough to burn you, nor will the bubbles formed be so violent that they spill out of the tube. However, it's best to keep aware of your surroundings and try to minimize spills and tube breakage. Once you've solved the mystery of the unlabeled solutions, check with your lab instructor to see if you've got it right. Have fun!